Okay, so let me start very briefly recapping what we did last time. So the key formulas which you all already have in your notes were these three. So this was describing how a particular source, so that a particular quadrupole moment, a time-dependent quadrupole moment, sources a gravitational wave. So those are essentially the two conditions that we need, and it needs to be time-dependent, and it needs to have a quadrupole moment. Spherical symmetric configuration won't do it. Then, as a next step, we computed the energy momentum tensor associated with these gravitational waves. Yeah, so we found that at second order, the gravitational wave back reacts on the background metric. So we cannot no longer work with a flat background metric. So it was the second order contribution from G mu nu that averaged over some intermediate length scale, which gives us this energy momentum tensor, which means that we always have to live also with these averaging brackets in our end result. No way getting rid of them. And then finally the power, so really the energy emitted per unit of time, can be computed essentially by combining these two formulas. So it can be expressed either as the first derivative of the gravitational waves or as the third derivative of the quadrupole moment. What we'll do today is have a very concrete system, binary system, so just like the thing that LIGO detected, and see explicitly how these equations work and actually predict something that we can measure. Any questions on last lecture? Okay, then we move to today's lecture. So the system we'll be looking at is point masses on a circular orbit. Okay, so we have two masses, M1 and M2, which are flying around in a circle. We're going to place this in the xy plane. The positions of these masses are R1 and R2. And then what we'll also need is the relative vector in between. So R is R2 minus R1. Capital M is the total mass. And mu is, as usual, the reduced mass. Okay, and this is, of course, a system you know very well, just from theoretical mechanics. And you know that these two masses, that there's a stable orbit around which these masses will rotate. That's the Kepler orbit. And the frequency of the Kepler orbit, so the frequency of the system, is just given by Newton's constant, the total mass, divided by r cubed. So we can write the Lagrangian of the system, or the energy of the system, as the movement of the center of mass. Okay, but so this is the capital R is the vector associated with the center of mass, but that won't give us any gravitational waves, because there's no quadrupole moment in the movement of the center of mass. So we can forget about that. Then we have the kinetic energy associated with the reduced mass. And then we have the potential energy. And we can make a change of variables. We can define a new R variable where we scale the mu inside so that we have a canonic variable. In terms of this canonic variable, let's call this, I don't know. So it should be hat and vector, but that's a bit awkward, and then dot, so that's a bit awkward to write, so I'll just remove the hat, okay? But this is a new variable now. which is just given by square root of mu times the original r. And in these units, the potential energy is given by this combination. Okay, so you immediately see two things. You see, we're dealing with a one-body problem. Yeah, in the end, there's only one vector we're dealing with. And there's only a single mass scale, which is given by this combination. Right? So in order to have it in the correct units, what is called the chirp mass, and why that will become clear in a moment, is mu to the 3 m to the 2. Okay, so that's just a dimensional parameter associated with this. And anything that we will compute will essentially can only depend on this mass parameter and on nothing else. Okay, so let's look at the gravitational wave emission. So that's this equation here. So what we need to do is we need to compute the quadruple moment. So we can say, okay, the position, say the position of this guy here, says an x and a y position, and of course it's just given by this frequency. So x of t just r cosine omega t, y of t r sine omega s of t. The quadrupole moment, just to remind you, was given by d3x xi xy t 0 0. Where in the end we will want to look at the traceless component, so the one with the slash. Oh, there should be a. Is there a slash here? No, slash comes later. Okay. And this thing, the energy momentum tensor, because we're in considering a non-relativistic signal, this is just mu. Okay, this is just the reduced mass of the thing. So now you can just compute. I mean, this integral is trivial, right? Because here it collapses. These are essentially delta functions. So I xx gives you mu r squared cosine squared omega st, which is nothing else than mu r squared over 2, 1 plus cosine 2 omega st. Then we need I y, which is the same thing with a sine, which means that here it's the same thing, just with a minus sign here. And the last one is I xy. So mu r square, there's a cosine, there's a sine. So that is just mu minus mu r square over 2 sine of 2 omega t. Okay, now we take, in the formula I just erased, right? In order to get the gravitational wave, we need the second time derivative of this object. So let's look at Ixx, take the second derivative. So that just brings down 2 powers of omega and a minus sign. And that is, of course, exactly minus I yy double prime. So that already tells you that this I double prime object is traceless. So we can interchangeably use I and I slash, as long as we are looking at a gravitational wave, or as long as our observer is on the z-axis. Okay, because along the z-axis, the projection operator just projects into the xy plane. So if we have this condition, it means we're already in the projected transverse traceless thing. So, yeah. So I double prime is I double prime slash if the observer is sitting on the z-axis. And then, okay, for completeness, the xy component okay, so with that we can now look at the gravitational wave signal. Yeah, so we learned there's two polarizations. There's a plus and the cross polarization, right? Where essentially the plus polarization is given by the diagonal components and the cross polarization is given by the off-diagonal components. So let's start with the plus. So transverse trace gauge, we're looking at some time t and at some position along the z-axis. Or it should be, we put it like this, some distance along the z-axis. So this is now the distance from the source to the observer. Okay, not to be confused with this other arc, which was the distance just between the sources. So this is essentially the formula I just erased. And here, because we're looking at the plus, all we need is the I slash xx double prime. Okay, so this of course we can just now we just insert. And what we're going to use is, because we don't here we don't like having, we want to express everything in these coordinates, so we want to keep the frequency here, the Kepler frequency, and we want to keep the chirp mass. Okay, I want to eliminate this r using this relation. So then we get here is minus 4g to the 5/3 distance to the observer. Chirp mass appears, chirp mass appears also with the to the powers of 2/3. The frequency 2/3. Okay, so there's several things to note here. So one is that the frequency of the gravitational wave is twice the orbital frequency of the system. Yeah, this is essentially reflecting that we are dealing with a spin 2 particle. Then we have here that the gravitational, so the amplitude of the gravitational wave scales with the frequency. Okay, so a higher amplitude. Let's put it the other way around. If your things rotate faster, it means you end up with a higher amplitude in your gravitational wave. And as expected, the only dimensional for there's the only two dimensional full parameters are the chirp mass and Kepler's frequency. And of course it scales as 1 over distance, well that's just the usual scaling with the sphere of the size of the sphere. And then of course you can do the same thing with the cross polarization. And you get the same thing. There's no minus sign here. And you get a sine instead of a cosine. So this is essentially the signal you would get from two black holes circling each other. This is kind of the type of signal you would then try and detect with LIGO. Yes?
Could you repeat that comment that you made about the effect that tells you it's a spin 2 particle?
Well, okay, so what you see here is that the frequency that you get is twice the frequency at which the system rotates. Okay, and we just got that out of the computation. I didn't do anything fancy, right? It was just a fact of writing the cosine squared as cosine of 2 omega. Yeah, but kind of the deeper reason for that is that it's a spin 2 particle. Yeah.
So the whole stuff is now done only for non-relativistic
Yes.
calculations.
Yes.
Just holds if they are very far apart, I would say.
It holds until pretty close to the end. So it's true that this breaks down in the last few cycles. So it's 2 or 3 or so. Yeah, and in order to deal with that, so essentially this is the leading order effect and an expansion in V over C. And then one can refine these calculations by going to higher order in that expansion. And that's precisely what is known as a post-Newtonian expansion. And people are working on order 4.5 or something at the moment.
But don't we also need to worry about strong gravitational effects, just not like strong velocity effects?
Well, we didn't specify what our background. Here we didn't specify what our background metric is, right? So as long as the perturbation is small, we're fine. But I mean, it is true that if you want to redo the full thing, like once you're, what we'll see in a second. What we see in a second is that what we predict from here is that the frequency will diverge as these things become arbitrarily close. Yeah, so that's something which is not physical, and there's of course some physics preventing you from actually hitting that divergence. And that physics is precisely that the black holes are really getting so close that they start touching. Yeah, and then we cannot treat these as point-like particles anymore. So that will kind of provide a natural cutoff for the theory. But yes, you do need strong. So you do need to worry about really strong gravity effect. But that's really when the two black holes get really, really close, when they actually start merging. Yeah, the actual merger you cannot describe in this way anymore.
So before that, Newton's gravity is completely fine.
Yeah. Yeah. Like up to the velocity effect. Yeah. I'll give you some numbers later on how fast these guys really are. Okay, there's another thing we've neglected, and that we've been essentially working we've been assuming overall Minkowski background, right? So at the very least, we need to take into account that simply in the time that the gravitational wave propagates from the source to us, the universe is expanding. And so there's going to be a redshift of the gravitational wave. For the events that we've observed so far, this redshift is actually very small. It's like 0.1 or something. So it really doesn't matter a lot. But on the other hand, it's like once you see the expressions, you will immediately understand why they look like that. So this is essentially the redshift, or let me say more general expanding universe. So in all our expressions, we'll have to replace the chirp mass with essentially a co-moving chirp mass, which is a function of the redshift of the source, which is just 1 plus z times the original chirp mass. The distance to the observer becomes the luminosity distance, which is just 1 plus z distance from the observer. And the frequency redshifts in the usual way, so you have f divided by 1 plus z. Okay, so that's simply the effect of the expanding universe on the propagating signal. And the interesting thing is that the things you observe in the end, the quantities you observe are, of course, these quantities here. Okay, so you have to be aware that there can be potential degeneracies between observing objects which are either far, like at high redshift, or at heavy mass or something like that. And there's another effect, and that is, so far we have considered these objects to be on the xy plane, and we've put the observer on the z-axis. Nature is, of course, not always like that, right? I mean, it could be that we observe a rotating system under a certain angle. And once we do that, the projection operator that we could just drop does, of course, something non-trivial, because it has to reduce the signal. So this projection effect, so if we have a gravitational wave, so we still have our black hole system in the xy plane, but the observer is now at some angle theta from the z-axis. So taking into account this effect and this effect, the final expressions that we get the R gets replaced by the luminosity distance, the M gets replaced by the curly M, and here we get a 1 plus cosine squared of theta over 2. This is the projection effect. And here this becomes, so 2, I just replace omega by 2 pi f, but then it should be 4 pi f. Should be 4 pi f. Okay. 4 pi, the frequency of the gravitational wave, times time. And the same for the cross polarization. Here we get a cosine theta, and here we get the sine. Okay, so with this, let's now look at the quadruple formula. So the energy emitted, the power emitted, the energy emitted by the system in form of gravitational waves. So that was the other formula which I erased. So that was just telling you the power is given you by the third derivative of the quadrupole moment. So we have the quadrupole moment in the x, y, y, xy, and so on. We're now again working. I'm working now again in the system where I put myself on the z-axis. Okay, so I don't have to worry about these projection angles. And of course, here we computed exactly the objects. So all we need to do is take the derivative of these. So the power emitted in gravitational waves . So we have the diagonal components. So it's the third derivative, and we have the off-diagonal components, third derivative. Okay, we just insert these equations, take the derivative, insert these equations. You see, get a cosine squared plus a sine squared. Okay, so this angular dependence will cancel out. So you get 2g 5c squared, this prefactor, then the prefactor from over there. So that's 4 mu r squared omega s squared times 1, cosine squared plus sine squared. And then again, you don't want to want to eliminate this parameter r and the parameter mu by using the chirp mass and Kepler's frequency. So in total, you get 32 g to the 7 thirds 5 c to the 5 chirp mass to the power of 10 thirds and frequency also to the power of 10 thirds. Okay, but what does this mean, right? This means that we have slightly cheated ourselves, okay? Because we started with a system where we said, okay, they rotate on a fixed orbit, which is given by Kepler's orbit, right? But now we computed that there's some energy loss, right? But the way you derived Kepler's orbit, you assumed energy conservation, and that's the only way you get Kepler's orbit, right? So if you have an energy loss, I mean, you can imagine some type of friction. This orbit will no longer be stable. Yeah, it will actually slowly decrease. But we also saw that as the orbit decreases, if you look at Kepler's frequency, you will see that the frequency increases. But as the frequency increases, we saw that the amplitude of the gravitational wave increases, and consequently, the energy loss in the gravitational wave increases. Yeah, so it's really a runaway system. You know, once you start emitting gravitational wave, your orbit starts decreasing, your frequency starts increasing, and your energy loss starts increasing. So once you start losing energy into gravitational waves, you start losing more and more and more energy, and your orbit shrinks faster and faster and faster. So the signal, we can already just qualitatively see how the signal will look like, right? So, and then we'll do it more carefully, but the gravitational wave signal, as a function of time, it will be oscillating, and then it will start to oscillate faster, while at the same time increasing in amplitude. And here, at some point, something has to happen, right? And what happens here is that we hit the innermost stable circular orbit, the ISCO, which is really when the two Schwarzschild radii of the black holes, or if you want the two normal radii of neutron stars, or whatever you're colliding here, they touch, right? And then, of course, you cannot compute things in this way anymore. And this is, in fact, I mean, this was precisely kind of this loss of energy in binary systems is what I was mentioning the other day, the way gravitational waves were first indirectly detected. Yeah, this was Holtz and Taylor. In 75, and they got the Nobel Prize for that in 93. So there's already been 2 Nobel Prizes for gravitational waves. Okay, but now of course we have to take this. I mean, this was just a qualitative picture, right? Now we need to understand how exactly does the frequency increase and how does the amplitude increase. Any more questions so far?
Yeah. So that expression is really is exactly that. The last one, the power. Yeah, but it's just that the frequency changes with time.
Yeah.
It's the only thing.
It's essentially the only thing, because the thing is, okay, so we're lucky in the sense that the gravitational wave, like the frequency of the gravitational wave, or if you want, the frequency, there's a time scale associated with this rotation, right? And there's a time scale associated with the shrinking of the radius. Yeah, and luckily, the time scale associated with the shrinking of the radius is much slower than the time scale associated with the rotation, right? So we can it's still a good approximation to assume that your radius is kind of constant to compute the frequency emitted at that time. But now we have to take into account that over long periods of time, that changes. So essentially the difference, okay, here, this is of course an extreme picture because we're showing the very end, but like if you look at here, all of this in spiral phase, the frequency from here to here doesn't change a lot. But yes, we are making a mistake if we apply these formulas at the very end.
My question on these 2 amplitudes, so the H plus and the H cross. So if you just look at the angular theta, so for H cross, it can happen that the amplitude just vanishes if we insert theta factorization, it's never the case. I mean, it's always there. But if I just look at the plus and cross correlation, it just seems that they are shifted by 45 degrees. So I don't get quite why one polarization just vanish and the other is always there.
That's a good question. Okay, so it does make sense that they vanish if you're looking at the system completely from the side, right? Then I think you should not see the gravitational wave signal. So I'm wondering if this should be a minus sign. No, but that wouldn't help either. I need to think about it, because also in reality there should be two angles. Well, okay, because if you want to actually detect the gravitational waves, then there's essentially two angles, right? There's one which describes what is the direction that the gravitational waves comes from, and the second which describes what is the orientation of your detector, right? Because your detector always has to consist out of two masses. I don't see it right now, but let me look it up until tomorrow, until the weekend in the discussion session this afternoon. Because I do agree, they should either both vanish in some direction or none of them should vanish, I think. Okay, so we've computed here a rate of energy loss. So what does that mean precisely for the energy of the system? Okay, so we can compute the energy associated with the Kepler orbit, which is a component in kinetic energy and is a component in potential energy, and we can express them again using the chirp mass and in particular using Kepler's frequency. And you find this is given by -1. This is essentially the binding energy of the system. 2/3, 2/3, 5/3. You need this in a second. So now if we compute the energy loss per time, we can do this in two ways. And we can use the formula we derived on the right board, because this is nothing else than the power. Or we can use this equation by just taking the time derivative with respect to omega. Okay, and now recall that the frequency of the gravitational waves is given by twice the frequency of the system. So it's 4 pi omega s. So then just by comparing these two lines, you immediately find a differential equation for the frequency in gravitational waves. G mc c to the 3 to the power 5/3 and f GW to the 11/3, okay, which tells you the rate at which the frequency changes increases as a function of f. So now you can just solve this differential equation, just separation of variables, and you find gravitational wave frequency. Okay, let's get some pre-factors. So these are m's, yeah, even though they look like pi's. 1 over tau to the 3/8, where tau is defined as the time measured from the coalescence time. Coalescence. Okay, so there's a time when they merge, and you start just measure time backwards from that time, and you see the frequency increases as 1 over tau to the power of 3/8. And this is the divergence I was talking about, right? If you send tau to 0, so if you actually approach the coalescence, this equation will tell you that your frequency diverges. And if your frequency diverges, it also means that your power loss diverges and your amplitude of your gravitational wave diverges. So luckily we don't reach that, right? Because there's a maximal frequency, which is twice the omega of the system. There should be also a 2 pi in here. At the innermost circular orbit. Okay, and you can compute this. Let's take black holes. You can compute this by simply looking at what is the distance at which the 2 Schwarzschild radii of the black holes touch. So for black holes, this would be 1 3 over square root of 6, 2 pi, c to the 3 g in the total mass of the system. Okay, so now we're nearly where I want to get. So the one more thing that we need is we have the energy loss over time, per unit of time. We need also the energy loss per frequency bin, because in the end your detector is going to be sensitive to some range of frequencies. Yeah, so you want to know how much energy deposit can you expect in the frequency band of LIGO. So that's just rewriting these equations in terms of frequency. So that's pi to the 2/3 GMC to the 5/3 F to the minus 1/3. And now what we can do is we can compute the total energy loss. Okay, because what is it? The total energy loss is the integral over dE dF from some minimal frequency. The minimal frequency is kind of when the system forms, until the maximal frequency, which is the frequency associated with the ISCO. And now, because this integrand grows very rapidly as a function of the frequency, it goes inversely with the frequency, like this. This means we don't care about the minimum frequency. Yeah, it's all determined by the maximum frequency. So you can compute this. Pi to the 2/3 2G GMC 5/3 F max to the 2/3. You replace this with you insert this, you replace this with slightly more clever variables, and you find that it is given roughly by 8 times 10 to the minus 2 the reduced mass of the system. Okay, which means, so for let's look at this for equal mass black holes. For equal mass black holes, the reduced mass is just 1/4 the total mass of the system. Yeah, so that tells you that if equal mass black holes merge, 2% of the entire energy goes into gravitational wave radiation, which is a huge amount. And this is only the amount, so this is correct up to an order 1 factor. Yeah, in reality, it's typically more like 4 or 5%. The reason is that here we've only computed the loss up until the maximum frequency, right? We've only computed the loss in gravitational waves in this in-spiral phase. Yeah, but there are then the actual merger, and then also what happens after the merger also emits gravitational waves, yeah, which is why this number is not entirely correct, but it gives you a very good order of magnitude estimate.
And this energy is just coming from the potential energy, not from the actual masses of the black holes.
Well, it's coming from both. It's coming from both because you will form a new black hole in the end. Okay, no, so yes, at this level it's only coming from the potential and kinetic energy, yes. But then when you also take into account the merger, then there's also actually mass conversion. Okay, any more questions? Okay. So one more thing I'd like to compute is the number of cycles. Okay, so the number of cycles is given by the time that I'm looking at divided by the period of the system, yeah, which is nothing else than f GW T dt. So that means we can compute the number of cycles between some T1 and T2 as integral f GV dt, which is nothing. Now we just rewrite this in terms chains of variables because I don't know what T1 and T2 is, but I know what f min and f max is. dfw f GW f dot GW. And now it's the other way around. So now it's the maximum frequency actually doesn't matter. It's the minimum frequency which governs the integral. So what I'm essentially asking is, I observe a system at a certain frequency right now. How many cycles does it have left until it reaches the innermost circular orbit, or so until it merges? So we can just plug in the expression over there for f. And what we get in numbers is, so for reference frequency of 10 Hertz, which is like typically when LIGO starts seeing things. And let's take a fairly light system, so a chirp mass of 1.2 solar masses. So if you observe a system with these properties, you know it's going to have another 10 to the 4 cycles until it merges. And correspondingly, if your system is much heavier, it has much less cycles left to merger. Okay, so things we did not take into account is we've assumed a circular orbit. It doesn't have to be like that, okay? It can be elliptic orbits. We completely ignored spins, meaning the angular momentum of the black holes. And we ignored any corrections, as we said, in V over C. Okay, so they are the 3 things which in principle need to be still taken into account in the in-spiral phase, and which lead to small modifications of what we've discussed so far. And then, of course, after the inspiral phase, you have the actual merger. That there's just no way around doing full numerical general relativity to describe that. And then after the merger, you have a so-called ring down phase, yeah, because you've created a new black hole, but the new black hole is not in its ground state. Yeah, so it oscillates, so-called quasi-normal modes, and that also emits gravitational waves. Yeah, and there is some sort of perturbative expression also for the ring down phase. So if you want to do the full thing, you can use perturbative theory at the beginning, you can use perturbative theory, different perturbative theory at the end, and full numerical GR in the middle. And they use this in order really to create these templates where for different input parameters, you know exactly what the waveform looks like. So how this amplitude, which increases and becomes faster over time, looks like, and then they match that against the actual data. Yeah, so fun fact, for example, about the ring down. So, I mean, because with the ring down here, you're really now probing the strong GR regime, right? You're really probing what is happening exactly at the horizon of the black hole. And there, for example, theories, I mean, can be debated how reasonable these theories are, but there are theories which say the black hole maybe does not have an horizon like a Schwarzschild black hole, but maybe it has something else, right? So here, when we're emitting gravitational waves, we're emitting them very close to the horizon of the black hole, right? So if it's a true horizon, some gravitational waves go out to the observer and some go in, but because it's a horizon, they just go in and that's it, right? But if there's some reflectivity on that horizon, if it's a very non-standard horizon, the gravitational wave could bounce off that horizon, and you kind of see an echo. You'd see an original signal, and sometime later you'd kind of see a second signal, which was reflected off the horizon. And because it's strong GR, there's a huge time dilatation in between the two. Yeah, so even if you only have a separation of a Planck mass or something, so super teeny, you could still have a visible separation in time. So this is, I'm just saying that because it's also really an interesting, completely new way to probe very fundamental ideas in physics. Okay, any more questions? Yes?
So would the gravitational waves which are generated between the center and the event horizon of a black hole, they would be trapped in the black hole?
Yeah, so the ones, right, so everything which goes inside the horizon will just be trapped.
And so this power that we calculated for the gravitational waves was for all of them. So a fraction of them would be trapped in the black hole.
Well, but a small fraction, because here what we computed, so what I was just saying is important when you look at the ring down phase, right? Because then you're really working on the horizon of the black hole. Here we're looking at the gravitational wave emitted by a system of two rotating point masses, right? So from that it is rotated, the gravitational waves are emitted just in a radial direction. Now of course it could be that the gravitational wave emitted from one black hole points directly in the object in the direction of the second black hole and is then emitted by that second black hole, right? But I mean, that's a very small probability of that happening. Yeah, so this effect is not important in the inspiral phase. I mean, in particular, at the beginning of the inspiral phase, right? The two black holes are really far apart. So it's really like 2-point masses. So these effects only become important when the two black holes are really close to each other.
But wouldn't all the gravitational waves be generated near the center of the black hole, because that's where all the mass resides?
No, because that's the thing. A single black hole generates no gravitational waves at all, because it doesn't have a quadrupole. You really need to look at the system of the two bodies. Otherwise, you don't get gravitational wave generation. So it's really the rotation of the two objects, not the black hole itself.
How do you reflect gravitational wave?
How do you reflect the gravitational wave? Well, not with standard physics, right? Not with anything.
I was wondering.
Not with anything you can build.
How do you reflect a wiggling space-time?
Yeah, so not with anything that isn't anyhow contained in general relativity.
Okay.
That's what I'm saying. I'm not sure how sane these theories are. I mean, there's also other reasons to debate these theories. But I mean, it's interesting that in principle, you can probe, you can look at things which you could never even think about looking at in any other system. Yes?
The effect of the spin on the waveform, is this really the way the spin is determined? Because the spins of these things are measured very well, no? With 10% accuracy.
Yeah.
So is that really from the effect you mentioned, sort of the spin correction?
Yeah. And you can, the thing is you can, so there's a spin correction, and the problem with the spin correction is that it's degenerate with the angle under which we're looking at the gravitational wave. Yeah. So they had this theta angle, which describes what is the plane relative to the observer, and then there's also the spin, but you only have so many observables, right? So there's a degeneracy. It's not a full degeneracy. The degeneracy breaks if you go to higher redshifts. So if you can actually determine the z, but for low redshifts, there's a degeneracy between the spin and the angle. So you can still, if you don't know either of them, you can still say something. But if you have some other ways of determining the angle, which they did, for example, for the neutron star merger, because they saw it in the optical frequency, so they had an idea of what the angle was, then you can determine the spin much better. But also what they measure is actually the projection. So what they can measure is the projection. It's not the actual spin, but it's the projection of the spin in the direction of the observer. So
it's always 0.7, it seems. Why is that?
Well, it's because there is a projection effect, right? So it shouldn't. I think it should be always fairly close to 0, right? I think it's the Skye effective. Well, we can have a look. So there's one parameter which is called Skye effective, which is the one they always give normally. And that is a projection of the spin in essentially the direction of the observer. So that being small always leaves two options. Either the spin can be intrinsically small, or you're just looking at it from the wrong direction. So that's why there's a bias in that observable. Any more questions? Okay, so now let's look at the actual events. Where did I stop here? Okay, so the first event was GW 150914. Okay, so this is year, month, day. And the fun thing about that event was that the first live observing run with the new detector was scheduled to start at exactly that day, 14th of September. And then 3 days beforehand, on the 11th, they decided to postpone the run until the 16th, because they thought they would not have everything ready. Then on the 12th, they actually did have everything ready. So they said, well, it's ready, let's turn it on. But they weren't officially, so they were in observing mode, but they were not officially in observing mode. And then on the 14th, there was a huge signal. So the signal was really, I mean, you've probably seen this plot, right? But they show here the amplitude as a function of time, and you have some noise, right? And then you have this signal, which is just like, I mean, it's just exactly like the one I drew on the blackboard, right? So you just look at it and you're like, yes, this is a signal. You see it in both detectors with 7 millisecond separation. So compatible with the maximal separation of 10 milliseconds that you can have. So people were thinking, okay, this is a fake signal, because what they were doing beforehand is they were injecting fake signals into the data to just train the analysis change, make sure everything works, but also train the people, right? So the people didn't know, like there were a handful of people who knew that there was a signal injected, but everybody else didn't, right? So for everybody else, it would just look like a real signal, and they would do the entire analysis, and then at the very end, they would say sorry, that was us. So given the timing of that, that was the biggest worry was, because the rumors about this were out pretty quickly, but just given the timing of it, people were, okay, come on, this is not real, right? This is, and this is a fake signal. But no, it was a real signal. It was not injected. So they got super lucky that like this first event was such a clear event, because it had a signal to noise. So they had to then continue. So they had this signal. You look at it, you see what it is. But in order to claim detection, you need 5 sigma, right? The way they do the analysis is they look at the actual noise data, right? And then they do the statistics on the noise data, and they need to say, okay, with like how many years of noise would you essentially need in order to produce this by coincidence? But in order to do this, you need noise, right? So they needed a minimum of 16 days of noise to get something which is at least 5 sigma, right? So until now, like this has never happened, right? So they don't know how big the significance of this signal actually is, but they needed 16 days of noise. So they needed to continue running for 16 days, hoping there would be not another signal, so that you could then actually claim a detection at bigger than 5 sigma. And then the significance then was 5.1 sigma, which means you would need 230,000 years of noise in order to get that by coincidence. And this was picked up by 2 different searches. So one was just the generic search, which is just looking for unusual spikes. This is so obvious that you see it. And the second search was really this template search. So they have a database of 250,000 templates, which are essentially computed for different masses, different spins, everything. And then they match against the data stream, and they pick it out. And the idea is to do this in a fully automated way, so that you can then alert other observatories very quickly, so that they can also go look for optical counterparts. That didn't work very well in the first event, but it then worked better later on. So, yes?
After the ESCO in this event, what information do you get from the black hole?
It helps. Okay, so it helps to break degeneracies. Yeah, so it helps with this spin versus observation angle thing, and it just helps to make sure that you have all your parameters exactly right. It also helps to break the degeneracy with the redshift.
But was this event enough? After the ESCO, was the statistics enough for?
They saw so it was fully the merger was at 144 hertz, which is nicely inside the LIGO band. So they saw the whole. They saw. Let me think. They saw the inspire. They saw the merger, the actual merger. I don't think that they had much data on the ring down. I think the ring down might have been just in the noise. I'm not entirely sure. So the frequency. So it came into the LIGO band at 30 hertz, and then it went up to 144 hertz. They were very heavy, right? So they were, the masses were 36 and 29 solar masses, which was slightly heavier than was expected at that time. That's why all the reference formulas, right, were for things something like that. And then this guy comes along. That means we got, and you can see now with these numbers, you can check that the formulas that we derived, even though we did not take all the effects into account, that they are pretty accurate, right? Because you can now see that here you get about 8 cycles to start from 30 hertz and these masses. So you can check that immediately against the formula that we had there. The speed of the black hole, so V over C, so it started at 0.2. 0.2, you can say, okay, maybe this is maybe an acceptable expansion parameter. And then it went up to 0.55, essentially just before the merger. So then you would say you really need to take into account the correction effect. So the emitted gravitational waves, the number you've probably heard, so it was 3 solar masses, which is crazy. And so so then there's a peak, so associated with this, there's a peak luminosity. And the peak luminosity in gravitational waves at that time is 10 times larger than the combined electromagnetic luminosity of all stars and galaxies in the entire observable universe. Yeah, so that's of course is not quite a fair comparison, right? Because the stars are there the whole time, and this guy was only there for a fraction of a second. But it's a huge amount of energy, so it was a huge event. Here you even have the spin parameter. So here this Skye effective parameter, which is the spin parameter, was minus 0.02, but with some fairly large errors, right? So essentially compatible with 0. And the distance was 400 megaparsec, which is kind of far in terms of astronomy, but it's not far in terms of redshift, right? So the redshift at 400 megaparsec is still 0.1 or something. So that's not a big correction at that time.
So what's now the definition of this? It's like difference in the spin of the total system, or
it's a combination. It's a combination of the. It's a combination of the individual spins, and there's also a projection effect, because you're looking at it under a certain. So it's a combination of the individual spins and the angular momentum of the full system.
is this also the spin for the final black hole, or is it?
No, that could be different. That could be different. I mean, you have angular momentum conservation, right? But the way this is defined, I think this is not immediately the spin of the final black hole. But I'd have to look up the exact definition. I was not planning to talk about it until he asked, so but I can look up the exact definition. Okay, so then we had more events. We don't need to go through all of them, but there were. Okay, but let me just briefly mention them at least. So there was another one in 2015 on Christmas. Nice Christmas present. Better than the diphoton Christmas present. So these are all the black hole events we had so far. So these were 14 and 7.5 solar masses. So these were much lighter, right? Which means in particular that here we had only 8 cycles because they were so heavy. These are much lighter. So if they're lighter, you see we get more cycles. So here we had 60 cycles in band. So a completely different type of event, right? So this one you could see by eye. This one, the amplitude was much smaller. But there were many, many more cycles. So you couldn't see it by eye. If you just looked at the data, you would see nothing, right? But I mean, if you do the proper statistical analysis, you can find a signal which oscillates many times before you see that it merges. Yeah, so you gain because you have a huge signal to noise ratio in a short time. Here, this was like in band for several minutes, and you kind of gain because you observe it for so long. Okay, then the second one was fairly heavy again. This one was another light one. I mean, of course, there's also bias here, right? Because if they're very light, we simply don't see as far. So, and this one was interesting because it was seen by LIGO and Virgo. Yeah, this is the first one that was also seen where Virgo was also operational, fully operational. And that means we have 3 detectors watching. And that in particular meant that we could do a Skye localization. Right? Beforehand, with just LIGO alone, the localization in Skye was essentially 1,000 square degrees. Which if you tell that to an astronomer, please point your telescope there, that's not so good. So then it went down to 60 square degrees. Yeah, so really more than an order of magnitude increase. And also that allowed to test for extra polarizations. Right? So we saw that in GR, you only have the plus and the cross polarization. You can never have anything more. So what they could do with this event is that they could test if there was maybe some extra polarizations which would be pointing towards some beyond GR extension. and they found nothing, right? Otherwise you would have heard. Okay, and then a particularly interesting event last year. So this was special because this was not a black hole merger. This was most likely a neutron star merger. So they are much lighter, right? So they have masses. So one mass was something like 0.3 to 0.6 solar masses. M2 0.2, 0.4 solar masses. Which means this was in band also for many cycles, hundreds of cycles. It was in band also for 100 seconds, so essentially 2 minutes of observing time. And it was super close. It was 40 megaparsec away. So despite it being so light, because it was so close, it was also in the range of Virgo. However, Virgo didn't see it, essentially. I mean, not significantly. Virgo did not see it with any significance, right? So that essentially left two possibilities, right? Either Virgo was broken, right? But if Virgo was not broken, it means the position of this thing had to be in a so-called blind spot of Virgo, right? So there is an antenna pattern associated with these gravitational wave detectors. They're not equally sensitive in all directions, but they are fairly broadly sensitive, right? So the blind spots where they are have very poor sensitivity are pretty small, right? So they're essentially like along the plane of the detector. So the fact that Virgo didn't see it actually helped a lot in the Skye localization, and maybe even more than if they had seen it. So that allowed to do a very good Skye localization, and also send out an alert to the astronomical community to look in a very specific spot. And independently, there was, by the Fermi telescope, there was an event labeled in this way. So it was a gamma ray burst, same day. And the arrival time was 1.7 seconds after the gravitational wave signal was observed. Okay, so these were. I mean, the analysis changes fast, but it's not that fast, right? So these were observations made completely independently. But then, of course, they have an automatic program, and the automatic program realized, oops, maybe there's a connection. So the alert got sent out. So this sent out an alert, this sent out an alert, and then there was also a combined alert sent out. So then, like, everybody started looking in that direction. A lot of people were pretty annoyed because it was 9 o'clock in the morning in some parts of the Earth. So you have to wait 10 hours before you can do anything. The first telescope to see it was a so-called SWOPE telescope in the Atacama Desert. And then independently, 5 others saw it before it was then officially announced that there was a transient event. So there was essentially a dot on the sky, which was not there beforehand and which was there now, and which fitted perfectly in the location that this was pointing to. So this really says, okay, they had not only done a Skye localization within 60 degrees, but they had actually identified really the galaxy where this comes from. And if you identify the actual galaxy, I mean, then you have essentially perfect Skye localization. And you can also now very precisely determine the redshift and everything, because you can just look at this thing in the optical, right? So then they continued observing in the optical over 60 calibrations, and in all bands, right? So radio, optical, infrared, everything was just pointing in that direction. And so this was, of course, all officially secret. But you can imagine how secret it is if it goes out to 60 calibrations. And some of these web pages, like Fermi, for example, has what is public for Fermi is the observation schedule, right? So what you could see in this observation schedule is that suddenly the telescope was pointing somewhere else, and the entry there was saying alert by GW 170817. So it was not very secret. And they are still observing the signal. right? So because I mean the gravitational waves, they're gone and past, right? But I mean the neutron star merger, I mean that a lot of complicated neutron star physics happens. So like there was an immediate signal, which was the gamma ray burst, which Fermi saw. But then there's like also an afterglow, because then jets form and all sorts of stuff. So like there was stuff to see in all the different frequency bands for days and weeks and months after the gravitational wave event, and even still now they're still observing this galaxy and learning a hell of a lot about neutron stars. But I'm not a neutron star expert, so we're going to talk about some fundamental physics that we can do with this. And that is the speed of gravitational waves. Okay, so these things arrived at a time difference of 1.7 seconds, and they were emitted 40 megaparsecs away. So from that, you can say you can put a bound on the speed of the travel time, or the velocity of the gravitational waves. Right? GR clearly says they travel at the speed of light, but who knows if Einstein is right? So let's have a look. So delta C over C, 2.4 times, just give you an idea of the numbers, delta T normalized to 1 second, and then the distance normalized. Okay, so if they were emitted at the same time but arrived 1 second apart, we would know that the difference is essentially the relative distance 10 to minus 16. Yeah, because now the thing is, we know that these arrived 1.7 seconds apart. We don't precisely know how they were emitted, right? I mean, that depends a bit on the emission physics of the neutron star, right? So there is some logic to think the gravitational wave was emitted immediately, and then maybe like the gamma ray burst was emitted a little bit later, because it first had to form, it had to break through some sort of atmosphere, something like that, right? So a very, very, very conservative estimate is to put here essentially plus minus 10 seconds, yeah, because 10 seconds is a very long time in terms of the physics going on here. But so that would bring you down to 10 to minus 15, and you could even put 100 seconds. You still have a bound of 10 to minus 14, right? So it's really, I mean, you're not going to put 10 to the 10 seconds here, right? So if we use this 10-second estimate, we find 2 times 10 to the minus 15 is smaller than delta C over C, is smaller than 4 times, and this is the wrong way around, right? So I have to say the right thing. Yeah, also one of them shows a minus sign. Okay, I think it was right the way it was, and this was a minus. Yeah, because of course the 0 has to be inside. Yes, okay. So here on this side, we have the case that the speed of the gravitational wave is smaller than the speed of light. Now, this is something that was actually constrained beforehand. Yeah, the reason it was constrained beforehand is that imagine you have a very high energetic particle, cosmic rays, which travels very close to the speed of light. Yeah, so it has a speed which is larger than the speed of the gravitational wave, but smaller than the speed of light. So that will be allowed in that case. Then, completely the same way as Cherenkov radiation works. And Cherenkov radiation is the emission of light if the particle travels faster than the speed of light in the medium. So here, this cosmic ray would emit gravitational waves by the same mechanism, because it will be traveling faster than the speed of the gravitational waves. So simply the fact that we observe high energy cosmic rays puts a bound on the speed of the gravitational waves here. And that was not so bad, right? I mean, that was of a comparable to what we got here. But this bound, yeah, the bound on this would be the case that the gravitational waves are faster than the speed of light. That was essentially completely unconstrained. Yeah, so we went from essentially having no bound to having a super strong bound. And that killed a lot of theories. Yeah, so that was the big part of the story of extensions beyond general relativity, Hondensky theories, and a lot of things. Overnight, huge chunk of the parameter space just disappeared. So that was a really that field I think was dramatically changed by this observation. This also puts, of course, a bound indirectly on the mass of the graviton, right? Because that would also slow down the speed of the gravitational wave. And in numbers, the bound on the mass of the graviton has to be now smaller than 10 to the minus 23 electron volts.
So can you explain where the first equation came from? So why is it so strong?
Oh, just because it's so far away. So you know the arrival time. Let's assume it was emitted. At the same time, right? But it arrived 1.7 seconds at us today. But the distance is 40 megaparsecs. Yeah. So you really have to travel very close to the speed of light in order to not accumulate a bigger difference in time. So it's simply the distance what we gains. So far we've been doing these types of observations in the solar system, and now.
So this, is it so unexpected, this thing? Because from cosmology we know that the bounds are so severe on the modified gravity that.
Well, I mean,
even if they make sense. So.
that's a big if.
No, but
yeah.
From cosmology, the bounds are already so severe.
Yeah, but this cut away a big chunk of theories that were before alive were dead.
This will because cosmology will tell us that any modification of dispersion relation of graviton on a distance smaller than the Hubble is excluded. So which means that if I modify gravity, I can only modify dispersion relation at the scales much larger than the Hubble. And this is minuscule. And now, if I have that type of modification, any graviton that's a shorter wavelength would have a huge gamma factor. And so it's great that this is an independent test, but I don't know. My question is this really true that, there is a theory which cosmologically is okay, and this rules it out?
So that's a good question. So let me rephrase the sentence. There were theories which people claimed that were okay with all constraints at that time, and which were then no longer okay after this.
Yeah, that's right. That's not the question. It seems that cosmology already. So consistency of the theory is a different matter. But let's say there is a theory in which dispersion relation of the graviton is modified, right?
Yeah.
And immediately we know that modification should happen at the scale larger than the Hubble, because before it would be excluded by cosmology.
So what exactly would exclude it from cosmology?
For instance, let's say if you say graviton mass.
Yeah.
Let's say a normal graviton.
Yeah, but the graviton mass is the other direction, right? That's this inequality.
No, so
It's
graviton has dispersion relation that you showed,
yeah.
Right? The propagator of the graviton is 1 over t squared.
Yeah.
Okay, so now if I have a theory that changes gravity, it changes 1 over t squared plus something, right? So this something can be a mass or width or whatever, right? So you have to modify a denominator of the graviton propagator.
Yeah.
And you can parameterize this modification by a scale, right? So it's like it would be t squared plus something. And the question is, at what scale that something becomes important, right? So that something should be suppressed by a scale. And the cosmology is telling us that scale where that something becomes important cannot be shorter than the Hubble scale. And this already puts an extremely severe bound on the modification. So would be interesting if there is a theory that would pass that and still would be ruled out.
Yeah.
That would be fantastic.
Yeah, we can have a look. I know the papers which claim that there were a bunch of previously sane theories which were then ruled out, but we can check if they actually.
It would have been that these previous theories never paid attention to
That is entirely possible, right? It's entirely possible, but yeah.
For instance, but if you modify dispersion, let's say you have a consistent theory that modifies dispersion relation at the couple.
Yeah.
Then I think it's still okay with this, right? For the time being, maybe tomorrow, maybe accuracy would be much better, but.
Yeah. I mean, as soon as we see an event which is correspondingly further out, right, this bound will get better, right? Because,
Of course, yeah.
but I mean, I think the interesting part is like, for example, before they were already bounds on the mass of the graviton, right? But I mean, assuming a positive graviton mass, right? So that is only the left-hand side, right? So this is essentially nothing new, right? But what is new is what was claimed to be new is the right-hand side. But let's have a look at the. I mean, I know where to find these theories that were supposedly okay before, and we can check.
Yeah, I think graviton mass per se is fine because there's always its bubble.
Yeah.
I think the phenomenologically.
Yeah. Here, right. I mean, the bound that you get, right? I mean, now I have it in units of electron volts, so we would need to convert. But the bound on the graviton mass is 10 to the minus 23 electron volts.
Yeah, that's very high.
Yeah.
Cosmology gives you immediately 10 to the minus 43 electron volts.
Okay, so that would make this bound much more stronger than what is claimed.
Well, the graviton mass should be less than 10 to the minus 43 or 44.
Yeah. So that would mean that that cosmology puts a stronger bound on the left-hand side of this equation. Yeah. Right. The only other thing I wanted to say is that because also this event was seen by Virgo too, right? So again, you can check for extrapolations, and again they found nothing. Though the error bars are very big, right? So they could exclude that gravity was described by a pure vector-like particle, which we might have guessed that beforehand. But I mean, these things what I found kind of spectacular about these events is that we're so used to accumulating loads and loads of data with say the LHC, right? And then we learn something by doing statistics and looking at gazillions of events. And here we really had single events, which told us a huge amount of stuff. And in the future, we will also be able to do statistics on these types of events. So essentially, the next round of LIGO, they're going to increase roughly a factor 3 in the sensitivity curve. But that means you get a factor 3 cubed in volume, right? So it means you get a factor 3 cubed in number of events. So very soon, they will be really accumulating statistics on these things. And then you can actually really say something, right? So at the moment, people are saying, these are kind of heavy, and these are maybe kind of similar to these, right? Maybe there's some meaning in that, and maybe there's not. But I mean, once we have 100 of these, and we have a distribution, then we'll see if there's a peak, or if there's something unexpected or not, or if the distribution is as expected. And the same with the spins, right? At the moment, people are saying, the spins, they're kind of all a bit close to zero, but, well, they have huge error bars, and they're not very many yet. So it's too early at this point to say anything, but I mean, in the future, we will have more information on that. Okay, any more questions?
What's the upper bound for the masses of LIGO events? I think it was something like 100 solar masses, right?
Yeah, something like that. Yeah, so in principle, so the reason people were a bit surprised at these 30 solar mass guys, but it also depends if you ask, so some questions depend if you ask them before the detection or after the detection, right? So I would say before the detection, the general consensus was that black holes that form through normal stellar evolution would not really be heavier than 10 or 20 solar masses. Though, I mean, it's also true that there were also papers before the detection which said that they could be heavier, right? But they were just not, it was kind of not part of the mainstream knowledge. And then, now of course, after the detection, people have gone back to all of these star formation models, and now there's ways to make them that heavy, right? So, and ways which are not particularly crazy, like you need them to form in some low metallicity environment or something like that. So it's, I don't know. I mean, astrophysics has has some error bars, right? So I think at this point we just have to wait if we see more data, right? I mean, because the reason people were excited about this is the question of could they maybe, well, if you could not have explained them with stellar black holes, then there was the option they could be primordial black holes, right? Which would be super exciting. But I think at this point it's too early, right? I mean, if we continue observing, if we see 100 of these and we see some sort of distribution which looks like this, right? I mean, then we'll start wondering what's going on, right? But at the moment, I think we just need more data. And so correspondingly, in order to see, so in principle, LIGO can reach up to 100 solar masses or so. And also, I mean, the volume for this is very big. But the problem is you have no guaranteed sources there, right? Because you don't expect these guys from stellar evolution. So what would have to happen is that you had two heavy guys, they merged, and they merge again. And then the third time they merge, you would see it as 100 solar masses, right? So it becomes increasingly unlikely to see.